Jai Hind, dear students. I'm Dr. Preeti, and here we are back with another video of metals and non-metals. In the previous video, we have seen about the physical and chemical properties of metals and non-metals and how metals reacts with non-metals that we have all seen in the previous video. Today, we are going to see about metallurgy and extraction of metals from the ores. But first, I would like to tell you one more thing about the reaction of metals with acids. In that, I just forgot to tell you one point, that is about aqua regia. We have seen yesterday that when metals react with acid, they produce hydrogen gas. But the least reactive metals like silver, gold, platinum, they are not going to react with any of the acids. So how can we dissolve them? We can dissolve even the least reactive metals like gold and platinum using a solution known as aqua regia. Aqua regia is a solution comprising of three parts of concentrated hydrochloric acid mixed with one part of concentrated nitric acid. Three parts of concentrated hydrochloric acid is mixed with one part of concentrated nitric acid, and that will result in aqua regia. This is such a powerful solution that it will even dissolve platinum and gold, which are the least reactive metals. Okay. Next, we will see about how we can get the pure metals from the earth crust. Metals usually occur on the earth crust in the form of oxides. Why they occur as oxides? Because oxygen is highly abundant and oxygen is very reactive also. So most of the metals we get in the earth crust is usually in the form of their oxides. Some other forms are also there like sulfides, carbonates are also present. But now how we will get these pure metals from the earth crust, that we'll see next. So when these metals are present in the earth crust, they are known as minerals. And from these minerals, if we can extract the metals profitably, because they are present in such a huge amount that we'll get profit by extracting them, such places where these metals are could be extracted profitably is known as an ore. Okay. Now we'll see from different ores how we will extract the metals. This also we'll see based on the reactivity series only. So first we'll start with the extraction of metals that are low in the reactivity series. Less reactive or low reactive metals, we'll see that how we can extract them. So if we take the example of the least reactive like gold and platinum, they are very less reactive. So usually they are present in the free state only in the earth crust. But if we see about copper and mercury, then they are usually there in the combined state. First we'll talk about mercury. So mercury usually occurs in the form of either oxide or sulfide ores. If we have a sulfide ore, then what we'll do, we'll heat it in presence of oxygen and we'll get mercury oxide and sulfur dioxide gas will be formed. Okay, I'm not balancing it, that you can do very well. So mercury sulfide is there, we heat it in presence of oxide, we'll get mercury oxide and sulfur dioxide. Then what we'll do, whatever mercury oxide we have got, we'll heat it further. Here also we are heating, this is triangle is showing the symbol of heating. So we'll heat it further and we'll get pure mercury and oxygen will be liberated out. Since these are very less reactive metals, so easily they could be separated from their oxides or sulfides. Not much efforts are required for that. So that is how we can get pure mercury. And ore of mercury, that is, we have seen sulfide, mercury sulfide, that is known as cinnabar. Okay, remember that. It can come as a 1 marks question. So what is the ore of mercury called? That is known as cinnabar. So that is how we can get mercury. If we talk about copper, which is more reactive than mercury, then what we can do is, if we are having copper sulfide, then we will make it to react with oxygen and we'll get copper oxide, and similarly sulfur dioxide gas is there, so it will be liberated out. These are all gases that will be removed out. So now what is formed with us is copper oxide. We'll continue to heat it up. We'll continue our process. So copper sulfide was already there in the container where we are doing the reaction. Now what else is formed? Copper oxide is also formed. We'll continue to heat it, and now what will be there? This sulfur will be reacting with this oxygen to form sulfur dioxide, and we'll be left with our pure copper. This sulfur dioxide being a gas, it will be eliminated out, it will escape out, and we'll get pure copper. So that is how we can extract the metals present in the low reactive series. Now, one question that can come in your mind is, ma'am, in case of mercury, when we heated mercury oxide, we just heated mercury oxide and we got pure mercury. But why is the second reaction different in case of copper? Why copper sulfide and copper oxide is reacting with each other? This is because of the reason mercury was very less reactive, even less reactive than copper. You can see that. So when we made it to react with oxygen, quickly all the mercury was converted to mercury oxide and no more mercury sulfide was left with us. सारा का सारा जल्दी से कन्वर्ट हो गया, बहुत क्विक प्रोसेस था. जैसे सल्फर ने ऑक्सीजन को देखा, it left that it all the sulfur went with oxygen, just left mercury. But copper being more reactive than mercury, the reaction was slow as compared to that in mercury. So now what happened, when we were heating it, some amount of copper oxide was formed, but still some amount of copper sulfide was there in the container where we were doing the reaction. And so the reaction in the second case is different. I am telling all these reasons just so that you can remember that. Okay, you need not write that. No one is going to ask you why it is different. Okay, that's not given in NCERT book, so you are not expected to remember the reason, but it's science, so it's easier for us to remember the things if you know the reason. So that is about the metals that is present in the low reactivity series. Which metals we call as at low reactive metals? Whatever metals are present below hydrogen, we call them as low reactive metals. Now we'll talk about the metals that are present in the middle of the reactivity series. Which metals are considered as middle in the reactivity series? Zinc, iron, lead. In fact, tin is also there, not mentioned in the reactivity series, but tin is also there. So these are all known as middle reactive metals. Now we'll see how we will extract these metals from their ores. But before that, I want to add one more element here, and that is, so now our reactivity series is Karan ne car मांगी, ऑल्टो, कार्बन जेन फरारी, पापा बोले हंगामा क्यों, होगी आगे और पिटाई. Okay, so by that way you can remember this reactivity series. I have added carbon also. I'll let you know why I added carbon here. Okay, so zinc, lead and iron, we are going to see the extraction of these metals. These are present in the middle reactivity series, so they are middle reactive metals. Okay, middle in the reactivity series, and we'll see how we are going to extract these metals from their ores. Now these metals like zinc usually occur in the form of their sulfides or carbonates. Remember, it's very important. What we are seeing next is really a very important question for your exams. So zinc usually, all these metals usually occur in the form of either their sulfides or carbonates. If they are present in the form of the sulfides, what we are going to do, we are going to heat it in presence of excess of air. In presence of excess of air, we will going to heat it. What we will get? We will get the oxide of zinc and sulfur dioxide gas will be escaping out. This process of obtaining zinc oxide from the sulfide ore is known as roasting. That is known as roasting. Now, if it was not in the form of sulfide ore, but it was in the form of carbonate ore, what we would have done, if zinc was in the form of carbonate ore, we would have simply heated it in limited supply of air. No need to pass more oxygen to that. We simply heat it without passing any oxygen, that is, we call it as in limited supply of oxygen. And what we'll get? Again, we'll get zinc oxide and carbon dioxide gas will be released. Fine. This process of obtaining zinc oxide from carbonate ores is known as calcination. So you could be asked in your exam, what is the difference between roasting and calcination? Then you can explain this. So why we are getting the metals? We are trying to get the metals in the oxide state because it's easier for us to get the pure metal from their oxides. It's easier to remove the oxygen. So first we'll obtain the oxide of that ore, and then we'll try to get the pure metal. Okay. You need to remember that. So I'll be telling you some ways how you can remember that. Remember, C for carbonate, C for calcination. So for carbonate ores, we are using the method of calcination. Second thing, remember for sulfide, you can just remember roasting. है ना, दो नाम तो याद रह जाते हैं आपको. Again, one more thing you can remember this. If you heat zinc sulfide without passing oxygen, sometimes you can forget कि oxygen ज़्यादा pass इसमें करना था या इसमें करना था. So remember, if we are not passing any oxygen, then how will zinc oxide will be formed? It's not containing any oxygen. So how will zinc oxide be formed? So for that purpose, we need to pass oxygen. But in case of carbonate ores, oxygen is already there. So no need of passing more oxygen, and we'll get the oxide of zinc. Okay, this is just a way to remember that what is calcination and what is roasting. Now we have got the oxide. Now we want to get the pure metal out of that. So what we can do is we can make to react zinc oxide with carbon, and for that reason only today I have written carbon also in the reactivity series. Carbon is more reactive than these metals. So we'll heat it with carbon, and that will be carrying out the reduction process. This is known as the reduction of this ore. So why it is known as reduction? Because zinc oxide will be converted to zinc, and carbon will be taking the oxygen. So it is going to form carbon monoxide. So zinc oxide undergoes reduction, and there is oxidation of this carbon. That is why we call it as reduction of the ores. So by that way we can get the pure metal. Now instead of using carbon, we can also use aluminium, magnesium, calcium, any of the more reactive elements for getting the pure metal. Fine. But carbon is like not very expensive, so we prefer to take carbon, but in some cases we take the other metals also. For example, I'll tell you two more examples where we can use a more reactive metal to get the pure metal. For extracting a pure metal, we can take a more reactive metal, and you will tell me the name of that reaction. So if we suppose we have manganese dioxide, MnO2, we make it to react with aluminium, and what we'll get is aluminium oxide and pure manganese. This is a highly exothermic reaction. One thing, that two conclusions that you can draw from this reaction is that this is one of the example of which type of reaction? Displacement reaction. Yesterday also we saw. So a more reactive element is displacing a less reactive element from its compound. So such an example is of a displacement reaction. And remember second thing, that displacement reactions are also exothermic reactions because they liberate out a lot of energy. So displacement reactions are always exothermic reactions also. Exothermic reactions are those in which heat is given out. So it is an example of exothermic reaction. It is an example of displacement reaction. So one example you can learn, and that will be good for both the type of reactions. In this reaction, this is also a redox reaction, because in this reaction manganese oxide का क्या हो रहा है? That is undergoing reduction, that is removal of oxygen, and aluminium is undergoing oxidation, that is adding of oxygen. Fine. One more such example when a pure metal we can get by just using another metal, that is iron oxide. If we have Fe2O3, and you know that iron is less reactive than aluminium, so we make it to react with aluminium and we'll get Al2O3, that is aluminium oxide plus iron. This reaction is very important, very important. In this reaction, the iron that we are getting, that is in the form of liquid molten iron. It is such a highly exothermic reaction that the iron that we are getting in this reaction is in the molten state. This reaction is known as thermit reaction, and this reaction is used for repairing the railway tracks. Suppose we have a railway track and it is having some crack at one place. So we can't take out the whole railway track and send it for repairing. So what we can do is we can carry out this thermit reaction, and wherever the crack is there, at that place only we'll pour that molten iron that is being formed during the reaction. So this molten iron will go into that crack and fill up the gap. When it will cool down, it will solidify and our crack will be repaired. So this is thermit reaction, which is used for repairing the tracks. This is also an example of a displacement reaction as well as a exothermic reaction. Okay, so that's all about the obtaining the metals that are in the middle of the reactivity series. Now we are going to see how we can extract the most reactive, highly reactive metals from their salts. Most reactive metals like sodium, potassium, calcium, magnesium, aluminium. If we want to extract them from their chlorides or oxides, how we can separate that out? We cannot make it to react with carbon or hydrogen because they are less reactive than these metals. So what we do is we use a process of electrolytic reduction. Remember, its name of the process is electrolytic reduction process. Okay, in electrolytic reduction process, what we'll do, suppose we want to separate out NaCl. So what we'll do, we'll take NaCl in its molten state. Molten state means we have to heat NaCl to such a high temperature that without mixing any water, it is getting converted into its liquid state. That is molten NaCl. Now what we do, we will take two electrodes. We can take these two electrodes made up of graphite also, because carbon is less reactive, so it's not going to produce any hindrance. So we take two electrodes, we'll connect one terminal of the battery. We can put the switch also, one of the terminal of the battery to the positive terminal, anode, and the other is cathode. And when we'll pass current through this, what will happen? Sodium being positively charged, it will go towards the negative terminal. It will get deposited there because cathode is negative terminals. So it will go towards the cathode and that will be getting deposited at the cathode. Chlorine being negatively charged, it will be attracted towards the positive terminal, that is anode, and that will be escaping out from anode because it will form chlorine gas, and chlorine gas is going to escape out and we'll get the pure sodium. Now we need to remember this reaction also, what is going on here. So at cathode, what is going to happen? Sodium metal, which was positively charged, it will go at cathode, take up the electron because cathode is a negative terminal of the battery. It will take up electron from there and it will get converted to sodium. And chlorine, which was already negatively charged, it will go at anode. It will lose the electron because anode is positively charged. So it will lose the electron, give it to anode, and it will be getting converted to chlorine gas, and that gas will be escaping out. This process is known as electrolytic reduction. This electrolytic reduction could be used for sodium, potassium, sodium, calcium, magnesium, and aluminium. Even if we want to get from aluminium oxide, if we want to get pure aluminium, this is the process by which we can get pure aluminium also. So that is used for all the more reactive elements, most reactive elements. Now, how you can remember that sodium is going at cathode and chlorine is going at anode? You can remember it by one thing, that is master chef not available. Master chef not available means master for metal, sodium is a metal, metal will go at cathode, master chef metal will go at cathode, and non-metal, that is chlorine is a non-metal, that will go at anode. A for available, A for anode. So master chef not available. By that way you can remember that metal is going at cathode and non-metal is going at anode. Okay, this is all just one way to remember that. So by that way we have got our metals from their ores. But the metals that we have got like zinc, copper, tin, all these are still having some impurities. They need to be further refined. So the second step is that now we need to remove all the impurities from this metal that we have got after all these processes. So how we will do that? We will do it by electrolytic refining process. Remember that electrolytic reduction process we were using for most reactive elements to get these most reactive elements, that is in the first step, that is during the process of metallurgy. But electrolytic refining we are doing for metals like copper, zinc, which are less reactive, but they are there, and we want to get the pure form of that. We already extracted copper from the sulfide or oxide, but or carbonate, but we want to get the pure form of that metal. So by which method we can do that? That is by electrolytic refining process. So how we'll do the electrolytic refining? We will take, for example, we want to perform it for copper. So we will take a bad similar thing that we have done for earlier process. We'll take anode, cathode. So if whatever impure sample of copper we have got, that we will take as a big bar of that copper and we'll connect it to sorry, we'll connect it to anode. The impure metal we are going to connect it with anode, and we'll take a thin strip of copper only. Whatever metal we are taking, we are doing the purification of copper. So that particular metal only, a thin strip we are going to take at cathode. And in the solution also, in the electrolytic solution also, we are going to take a salt of that particular metal only. So here we are going to take copper sulfate solution. So now when we'll turn on the current, what will happen? The copper sulfate that is present here, copper being positively charged, it will be attracted towards the cathode because cathode is negatively charged. So it will be pure copper will from the solution will be attracted towards the cathode. Here anode is positively charged and a metal is also positive, so that will be repelling the copper. And here sulfate is there, so usko chhod ke ye copper ja chuka hai. So the other copper from this anode strip will be attracted towards the electrolytic solution by sulfate ions. So continuously what will happen? The copper from the solution, electrolytic solution, will be moving towards cathode, and the copper that is present at anode will be continuously moving towards the electrolytic solution. At the end of the process, what will be happening? This anode strip that we have taken as a bar, that will all become thin, very thin, because all the copper from anode will be moving into the solution, and from the solution all the copper will be moving towards the cathode. So thin copper strip that we have taken at cathode will become very, very thick. So that is how we'll get the pure copper at cathode. You remember now, metals go at cathode, master chef. So that will be there. Now what will be there? Some soluble impurities are there in this copper bar, some insoluble impurities are there. If soluble impurities are there, then that will be mixed in the electrolytic solution. But if some insoluble impurities are there, then that will get collected at anode. That will be getting collected below anode, and that is known as anode mud. That is getting collected below anode, and that is known as anode mud. Since we took a pure solution, impure copper at anode, so all the impurities whatever will be there, that will be collected below anode only, and that is known as anode mud. Now remember one thing, there could be two terminology similarly here, anode mud and one is gangue. What is gangue and what is anode mud? Anode mud is the impurities, insoluble impurities that we get after electrolytic refining process, that gets collected below the anode. What was gangue? The gangue is something that we obtain in the first step of metallurgy. When we take out the metals from the earth crust, they are having a lot of sand, dust, everything. So, by various physical processes, that just of washing away, we remove those sand and dust particles and the impurities that we remove in the first step without any doing chemical process, without just by doing some physical process like washing away or something. Then the impurities that were removed in the first step of concentration of ore, or known as enrichment of the ore, that impurities are known as gangue. And the impurities we have removed after electrolytic refining process, that is anode mud. Okay, I hope you are clear with both. One thing also you should remember, that this is electrolytic refining process, and the process that we have used for high reactive metals was electrolytic reduction process. Okay, similar terms but having a entirely different meaning. Okay, so if you want to take a screenshot, I'll just shift at the side and you can take a screenshot of the electrolytic refining process. From this chapter also you could be asked various diagrams, so prepare the diagrams very well. Okay, for example, reaction of water with metals, for that also a very simple diagram is given in your book, so you can practice that also. Okay, so all these diagrams also from the chemistry portion also, they are important. The next and the we are completed with metallurgy. Now the last topic is about corrosion. We have taken out these metals with all the efforts, but they may be spoiled by reaction with the atmospheric gases like oxygen, carbon dioxide, sulfur. They are all present around us, so they can react with our metals and the metals quality will be degraded, and that process is known as corrosion, the slow eating away of our metals due to reaction with oxygen, carbon dioxide, sulfur, etc. present in the atmosphere. This process is known as corrosion. For example, when we talk about silver, the silver gets black in color after sometimes we use it. So because of the formation of silver sulfide. Sulfide of sulfur is formed, and that when silver reacts with sulfur, that forms the sulfide of silver, and that only leads to tarnishing of our silver, that is blackening of our silver. Apart from that, copper also, if you use some copper jugs or utensils at home, you must have seen that a greenish layer starts depositing on our copper utensils, and that is known as that is because of formation of copper carbonates, because copper reacts with carbon dioxide present in the atmosphere, and that leads to the formation of carbonates of copper, and that only leads to that greenish layer. Apart from that, you must have all seen about iron. Iron gets rusted away. So iron reacts with the oxygen and water molecules present in the atmosphere, and it gets a flaky brownish layer over it. that comes out as flakes that damages our iron, and that is known as rusting. Now, rusting is a form of corrosion. Corrosion doesn't only include rusting. Rusting is one of the parts of corrosion. Remember that. Usually, when we ask corrosion, students just mention about rusting. So, tarnishing of silver, reaction of copper with carbon dioxide forming copper carbonate. These are all corrosion only. Okay. Now, how we can prevent the rusting of iron, or we can prevent the corrosion of different metals? How we can do that is, some of the methods of doing that is galvanization, anodizing, that we have seen for aluminium, that we perform anodizing. Apart from that, we can make alloys out of them. If we have iron, we can just simply paint it. So painting, grease could be applied over it, that is known as greasing. Or chrome plating is also done. Chrome plating means like in your cars or bike, you must have seen a shiny metal over it, you know, silvery colored metal. So that is of chrome plating. So that is all done to prevent the rusting of iron. So we will see what are alloys. Especially we are going to say about alloys. Apart from that, in galvanization, what is done, that also we are going to see. So in galvanization, we coat a layer of zinc over the iron metal. And you know that zinc is more reactive than iron. So if iron tries to react with oxygen, or if it tries to react with anything in the atmosphere, zinc being more reactive doesn't allow us to react with that, and itself reacts with that. So zinc, even if zinc reacts with the oxygen, that will not damage the zinc. And if that iron reacts with the oxygen and water, that leads to rusting. But no such effect is there on zinc. So zinc is coated over the iron. This process is known as galvanization. Now, apart from that, what we can do is alloying. So, what are the different alloys we make to prevent the corrosion of different metals? Let's see that. Let's see about some of the alloys. Again, very important as a 1 marks question. One of the alloys that we all use at home is stainless steel. Now, iron, if we take in the pure form, it's very stretchable, and it's soft also. It's not having that much hardness. We didn't knew now. We always imagine that iron is very hard, but it becomes hard because of mixing of some carbon in it. So we turn it into an alloy by mixing some carbon. So here we are mixing iron with a non-metal. So we will define alloy that by that way only. What is alloy? What are alloys? Alloys are a mixture of a metal and a non-metal, or mixing of metal with some other metals to change the properties of the original metal. So that is known as alloying. So if we talk about the alloy of stainless steel, that is a alloy containing iron, nickel and chromium. Iron, nickel and chromium, if you mix them together, that will form stainless steel. Apart from that also, whenever we want to take iron, we usually mix it with carbon. That will make it hard. If we make a bridge out of pure iron, then that iron bridge is just going to become a swing after some time, because when heated up, it stretches. So that, to prevent that, we mix it with the carbon. We'll take an example of another alloy, that is brass. Then we will see about bronze, then solder, and then last is amalgam. We'll see about all these alloys. So stainless steel is an alloy containing iron, nickel and chromium. Brass is an alloy of copper and zinc. Remember that brass is an alloy of copper and zinc. Have you ever seen brass at home? Yes, you have. Brass in Hindi, it's known as pital. So you must have seen the bells in your temple. That is all made up of brass, pital, the yellow colored thing. So copper and zinc are mixed to form brass. Next is bronze, which is an alloy of copper and tin. Tin is represented by Sn. Okay, bronze is an alloy containing copper and tin. Then solder is an alloy containing tin and lead. For lead we use a symbol Pb. So tin and lead, they are combined to form solder. Solder is used for joining of the electrical circuits. If you have ever opened your television set or your PC, at the back of that you can see a green board, and over that green board you can see small white dot like structures, some shiny dots. That is usually of solder, because when we join the wires we use the thing solder. Solder has such a low melting point. So alloys sometimes have very low melting point, like in case of solder. Sometimes they have a very high melting point, like we use in heating devices like nichrome. है ना? We are using it for heating devices, like we want to make a geyser or we want to make a immersion rod. So we take nichrome wires for that. That is also an alloy, but that is having a very high melting point. And here we see a solder that is having very low melting point. Okay. Next is about amalgam. Amalgam is an alloy containing mercury. If an alloy is containing mercury, that is known as amalgam. So we have seen about different alloys. These can come as 1 marks question. So you should remember that. How to remember that amalgam is an alloy of mercury? Remember A for amalgam and A for alloy. And in the beginning of the class, I have told you cinnabar is an ore of mercury. You can take a screenshot of this. Cinnabar is an ore of mercury. So usually students just get confused between amalgam and cinnabar. ठीक है, तो अगर और पूछा है तो that is cinnabar, and if you ask write the alloy, A for alloy, A for amalgam. By that way you can remember. Okay, so that's all about the chapter. I want to put up 3 questions to you. Think about the answers by yourself, but in the same video only I am telling the answers also. You can pause to think the questions. First is, if you take a spatula and you put some sulfur powder over it and you heat it, and if you bring a dry litmus paper next to it, what will be there? And if you bring a moist litmus paper next to that, then what will be the reaction? In which of the following condition you will be observing a change? So you have taken a spatula similar to a spoon only, and you have put some sulfur powder over it and you start heating it. So what will be formed is sulfur dioxide gas. Now you know that sulfur dioxide gas is produced. Oxygen, it will react with oxygen, sulfur will react with oxygen to produce oxides of sulfur. Now if we bring a dry litmus paper, no change will be there. But if we bring a moist litmus paper next to it, then what will be happening? That moist litmus paper is containing water and this will produce acid. Sulfurous acid will be there. Sulfurous acid will be produced, and since acid will be produced, that will lead to change in the color of pH paper or litmus paper. The litmus paper is going to turn red. Okay. So oxides of non-metals, we have seen that they are acidic in nature. So a similar acidic reaction we are going to see here. है ना? Acid rain भी ऐसे ही होता है. Next question of mine is that we don't take iron to make the hot water tanks. Instead of that, we take copper. Copper is used to make hot water tanks. Why we can't use stainless steel or iron to make hot water tanks? Because copper is less reactive than hydrogen, and you have seen that it will not displace hydrogen even from steel. Okay, even if you use steam, then also copper is not going to react with that steam. Copper क्यों react नहीं करा था steam से? Because copper is less reactive than hydrogen, so how it can displace hydrogen? So we make the hot water tanks out of copper and not with iron. Okay, and the last question is that sometimes you must have observed that your mother must have cleaned copper vessels with some tamarind or some lemon juice. So why these sour substances are used to clean the copper vessels? Shall I tell you the answer? It's because of the reason that these are acidic in nature. Lemon juice, tamarind, they are all containing the acids. Lemon juice contains citric acid, Tamarind contains tartaric acid. So what happens? These are all acidic in nature, and so the metals are going to the that will remove the carbonates from it, and we will get a pure copper. So these layer of corrosion or carbonate will be removed because of the action of these acids, and we will get the pure metal our carbonate as our copper. Okay, so that's all from the chapter. We have completed with metals and non-metals. Keep studying, keep scoring. Good day.